Mars is currently a frozen, bone-dry rock. Its atmosphere is too thin to trap heat, and its surface is a radiation-soaked desert where biological life, as we understand it, cannot survive. Yet for a decade, NASA's Curiosity rover has been climbing the slopes of a 5-kilometer-high mountain, searching for evidence of a very different world. Its mission is centered here, within the Gale Crater, exploring the ancient sediment layers. In June, the rover reached a valley that challenged our understanding of Martian geology. A 360-degree panorama revealed a landscape that looked far more structured than the usual jagged rock. Spread beneath the rover's wheels were thousands of uniform polygon patterns. This massive field of repeating geometry stretches in every direction Curiosity can see. These structures look remarkably biological. To anyone familiar with Earth's nature, the ground appears to be covered in a massive, fossilized beehive. The sheer scale of this formation is massive. It covers the valley floor and extends upward, disappearing beneath the heavy sand dunes of a nearby 6-meter-tall hill. Dr. Ashwin Vasavada, the lead scientist at NASA's Jet Propulsion Laboratory, noted that while the rover has seen small polygons before, this immense, unique fracture field is something the team has never encountered on this scale. This creates a significant paradox. Mars lacks the atmosphere for insects, meaning a massive geological process functioned as a biological architect, creating a structure mimicking life. Scientists are investigating 3 specific geological forces that could explain how raw rock organizes itself into such precise geometry. The first possibility is desiccation. This happens when ancient layers of wet mud settle and begin to lose their moisture. As the Martian sun baked the ground, the mud would have contracted and cracked, eventually hardening into these permanent geometric shapes. The second possibility involves a freeze-thaw cycle. In this model, ground ice beneath the surface repeatedly forms and melts over thousands of years. This constant thermal shifting creates physical pressure that forces the soil to organize itself into distinct, repeating hexagons. The third possibility is subterranean pressure. This occurs when geological forces build up deep beneath the planet's crust. Eventually, that pressure forces trapped water toward the surface, splintering the top layers of rock into the fractured patterns we see today. Researchers are currently testing the chemical composition of these rocks to identify the specific cause. Regardless of which process won out, they all share one requirement that modern Mars lacks: an active, repeating water cycle. The location of these fractures on Mount Sharp is significant because this structural evidence exists alongside a much larger chemical story. In this exact region, Curiosity identified carbon-based organic molecules. These are the specific chemical precursors required to build complex genetic structures like RNA and DNA. Whether these molecules were produced by ancient biology or complex geological reactions is still debated. However, the honeycomb field places these building blocks in a clear context. We now have the raw chemistry of life situated in the exact spot where liquid water once moved through the environment. Looking across these boulders, the honeycomb field serves as a physical record of the planet's history. These geometric scars prove that billions of years ago, the Gale Crater was a landscape defined by flowing rivers and active lakes. These formations confirm that the planet was once a wet and dynamic environment, in stark contrast to the frozen desert we see today. Curiosity has successfully linked 2 major findings: a climate capable of moving liquid water and the presence of the organic molecules that life requires. Curiosity has documented an environmental blueprint for a world that was once perfectly suited to support the development of life.